Hello everyone and welcome back to Tech Tangents, episode 124. I'm Jenny.
And I'm Mark. Jenny, I've been, pretty energized since NVIDIA's GTC conference back in March. There was just so much interesting stuff coming out of it.
Oh yeah? Energized, huh? That sounds promising. Anything in particular catch your expert eye? Beyond the usual, massive new chip announcements?
Definitely. Well, it's related to the chips, actually. We talk a lot about how powerful these ASI processors are getting, right? Like NVIDIA's latest Blackwell chips. Pulling, 1,200 watts each? Maybe even more, depending on the configuration.
Right. 1,200 watts. Which, for perspective, is already a huge times amount of power for a single component. Sounds less like a chip and more like a small space heater.
Exactly. And all that power converts directly into heat. Trying to pack dozens or even hundreds of these heat-blasting chips into a dense server rack? Well, keeping them cool is becoming a serious engineering challenge. The old ways, just blowing air across heat sinks, are really starting to hit a wall.
Okay, so the core problem is thermal management for these increasingly powerful AI systems. Where does the GTC conference come back into this?
Right, so one company that was making some noise there was CoolIT Systems. They specialize specifically in liquid cooling solutions, particularly targeting data centers and high-performance computing.
CoolIT. Okay, points for an appropriate name. So, liquid cooling. Is this basically like the setup some PC gaming enthusiasts use with the tubes and radiators, just scaled up? A asterisk lot?
That's the fundamental idea, yeah. Instead of relying solely on air moving over hot metal fins, you're actively circulating a liquid coolant directly over the hottest components, the processors, the GPUs, using specialized blocks called cold plates. It's just much more efficient at absorbing and transporting heat away.
Makes sense intuitively. Liquid carries heat better than air. Basic physics we probably learned back in high school, right?
Precisely. And at GTC, CoolIT was showcasing their latest generation of this tech, specifically highlighting their Omni split-flow cold plates. And here's the number that really got my attention. They're engineered to handle chips with a thermal design power, or TDP, of up to, 4,000 watts.
Hold on. 4 times 1,000 times watts for one chip? Mark, we just established that 1200 W for Blackwell already sounds intense. 4000 W seems, almost like science fiction territory for a single processor die right now.
It sounds enormous, I know. And look, maybe the very next generation won't hit times 400 W right out of the gate. But the crucial point is that CoolIT is building and validating cooling solutions that are ready for the next times big leap in processor power and the heat that comes with it. They're anticipating the roadmap.
Okay, so it's about future-proofing the cooling infrastructure, getting ahead of the curve. How do these Omni cold plates actually manage that kind of extreme heat load? Is it just, like, a bigger pump pushing more liquid faster?
If only it were that simple. It's more about clever fluid dynamics design, specifically something they call split-flow technology. Imagine the cold plate surface that sits on the chip. Inside it are tiny microchannels for the liquid coolant to flow through, right?
Okay, like miniature liquid highways right above the silicon.
Good analogy. Now, in a traditional design, the liquid might enter one side and flow across to the other. With split flow, they divide the incoming coolant flow into multiple parallel paths timed simultaneously across different sections of the chip surface. Think of it like splitting a river into several smaller, faster streams that cover the whole area at once.
Ah, I see. So instead of the liquid getting progressively warmer as it flows across a long path, you have multiple streams starting cool and covering their zones more effectively. This prevents parts of the chip from getting significantly hotter than others, especially on these larger, more complex AI processors that might have uneven heat generation.
Exactly. It leads to more uniform surface temperatures and much better overall heat transfer. They're claiming these Omni cold plates provide something like a 30% boost in thermal performance compared to more standard liquid cold plate designs, largely because of this improved efficiency and uniformity.
A 30% improvement in cooling performance. That sounds quite substantial. So, the practical benefit is that AI systems could potentially run faster or sustain peak performance for longer because they're not hitting thermal limits and throttling down?
That's the core idea. Less thermal throttling means more consistent, predictable performance from these very expensive, very powerful chips. It also unlocks another critical factor: density.
Right, the density factor. If you can pull heat away more effectively within the same physical space, you can pack more processors, more accelerators, closer together, more compute power per square foot of data center floor space.
A huge deal for data center economics. CoolIT talks about enabling server rack power densities far exceeding what air cooling can realistically handle. We're potentially talking several times, maybe even up to 10 times the compute density in some scenarios, compared to air-cooled equivalents.
Okay, the technology sounds impressive, the performance gains are clear. But what about the practical side? Isn't implementing liquid cooling like this a massive headache for the server manufacturers or the data center operators? It feels more complicated than just installing fans.
That's a very fair question, and it touches on one of the counter-arguments you often hear: the cost and complexity angle. It is undoubtedly more complex upfront than traditional air cooling. You've got plumbing, coolant distribution units, more potential points of failure,
and presumably a higher initial investment cost compared to just buying bigger fans or air conditioners?
Generally, yes. The initial capital expenditure can be higher. But companies like CoolIT are working hard to streamline the integration. One really key aspect here is their close partnership with NVIDIA.
How does that partnership help?
CoolIT is part of NVIDIA's Recommended Vendor List, or RVL. This basically means their cooling solutions are pre-validated and certified to integrate smoothly with NVIDIA's hardware platforms, like their MGX modular server system design.
Ah, okay. So it removes a significant chunk of the integration guesswork and compatibility testing for the companies actually building the servers. It's like getting an NVIDIA-approved stamp for the cooling component, ensuring it plays nice with the expensive GPUs.
Precisely. It reduces the engineering effort and validation time needed by server OEMs, original equipment manufacturers. CoolIT mentioned it could shave weeks, maybe even months, off the typical testing and qualification cycle.
That's a tangible business benefit, faster time to market. What about reliability, though? I mean, you mentioned plumbing. My brain still conjures up images of leaks near very expensive electronics. Is that still a major concern?
It's the classic concern, and definitely a focus area for these companies. CoolIT primarily uses what's called single-phase direct liquid cooling, or DLCs. The key thing here is single-phase. The coolant always remains in its liquid state throughout the cooling loop. It doesn't boil into a gas.
Okay. Unlike some other liquid cooling approaches I might have heard about, like two-phase or immersion cooling?
Right. Two-phase cooling involves the liquid actually boiling into vapor directly on the chip surface. This phase change can absorb a lot of heat, making it potentially very efficient, but it also adds complexity. You need to manage pressures carefully, deal with potential condensation, ensure consistent boiling. Then there's immersion cooling, where you literally submerge the entire server or components in a non-conductive dielectric fluid. That also has high thermal potential, but comes with its own set of challenges around fluid management, maintenance, and material compatibility.
So single-phase DLC, the approach CoolIT focuses on, is seen as maybe a more mature, reliable, and scalable option for large deployments, even if it's not theoretically the absolute peak of heat removal?
That's generally the thinking. It strikes a good balance between high performance, significantly better than air, and proven reliability using established pump and plumbing technologies just adapted for the data center scale. They use robust couplings, leak detection sensors, and carefully designed closed loops to minimize risks.
Okay, reliability is paramount. And CoolIT seems like they're not just a startup jumping on the AI bandwagon. They have experience?
Yeah, they've been around for a while, specializing in this area. They highlighted their global manufacturing footprint, facilities in North America, Taiwan, Malaysia, and these dedicated liquid lab innovation centers focused on design, extensive testing, validation, and getting all the necessary safety and operational certifications, like UL listing.
So they're trying to offer the whole package, collaborating on design, ensuring compatibility, handling the manufacturing, and backing it with testing and certification.
Seems that way. One of their executives, Brandon Peterson, was quoted saying something like, "Their split-flow architecture eliminates thermal throttling risks for next-general AI accelerators." That's a pretty confident statement.
Confidence presumably backed by a lot of simulation and testing, one hopes. So let's step back again. What's the bigger picture here? What does this kind of advanced, integrated liquid cooling really at times enabled for the future of AI and data centers, beyond just letting the chips run hot?
Well, fundamentally, it sustains the relentless push for more powerful computing. As AI models, especially things like large language models, get vastly larger and more complex, they demand exponentially more processing power. That means denser, hotter hardware. Efficient cooling isn't just a nice-to-have. It becomes the critical at times enabler for that continued progress.
It's like, you can design the most powerful engine ever, but if you can't stop it from melting, it's useless. Cooling keeps the AI equivalent of Moore's law, whatever that is now, actually functioning.
In a way, yes. But it also ties directly into data center efficiency and sustainability, which is a massive focus area right now.
Right, because traditional air cooling for these huge data centers consumes just enormous amounts of energy, often a huge portion of the facility's total power draw and carbon footprint.
Exactly. Liquid cooling, being much more targeted and efficient at heat transfer, can significantly reduce the energy needed specifically for cooling operations. Less energy wasted moving vast volumes of air means a lower power usage effectiveness, or PUE, score for the data center.
So it's not just about enabling faster chips, it's potentially a greener way to run them too? Less energy consumption overall?
That's a major part of the value proposition. Lower energy bills for the operators, and a reduced environmental impact. Plus, remember the density factor? If you need less physical space and less building infrastructure for the same amount of compute power, that also contributes to sustainability.
That's a good point. Though, playing devil's advocate for a moment, are there other environmental factors to consider, like the manufacturing of these liquid cooling components, or the life cycle and disposal of the coolants themselves? Is the overall picture always greener?
That's a valid point, and something the industry is increasingly looking at through full life cycle assessments. The coolants used in DLC are typically engineered fluids, often water glycol mixtures, or specialized dielectric fluids, chosen for thermal properties and material compatibility. Their production and eventual disposal do have an environmental footprint, no doubt. It's a complex equation, but the argument is that the operational energy savings over the system's lifetimes, especially at scale, generally outweigh the impacts of manufacturing the cooling hardware itself, particularly compared to the massive energy demands of air conditioning terawatts of compute.
Okay, so it's a trade-off, but the operational efficiency gains are expected to be the dominant factor. And I think I read somewhere about potentially reusing the heat captured by the liquid?
Yes. That's another interesting aspect. Because liquid absorbs and transports heat so effectively, the waste heat collected from the servers is in a much more usable form, warm liquid, compared to just diffuse hot air. This warm liquid can potentially be piped away and used for other purposes, like heating nearby buildings or office spaces, or even for certain industrial processes, turning a waste product into a resource.
Okay, that's genuinely clever. Using the heat generated by training the next big A model to warm the offices of the people developing it.
It's becoming a serious design consideration for new, large-scale facilities. And looking further ahead, people at CoolIT, like Neil Mulgy, another director there, are talking about the supporting infrastructure needed. Things like highly redundant, modular CDUs, that's coolant distribution units, the hearts of the liquid cooling system, designed to handle failures gracefully and scale up to support these future mega racks drawing hundreds of kilowatts.
So they're thinking about the entire ecosystem, the cold plate touching the chip, the pumps moving the fluid, the radiators or heat exchangers rejecting the heat, the monitoring systems, the fail-safes. It all has to work together reliably at an immense scale.
Seems like it has to. The plumbing, the distribution networks, the intelligent monitoring, it all needs to scale reliably alongside the compute power itself.
It really feels like we're witnessing a fundamental shift in how high-performance data centers are designed and operated, moving definitively away from just blasting everything with cold air.
I think that's right. Air cooling will certainly still have its place, perhaps for lower power components or in hybrid approaches. But for the absolute highest performance tiers, especially in demanding fields like AI and simulation, direct liquid cooling seems less like a niche experiment and more like, well, an essential requirement.
Interesting. So CoolIT and companies like them are positioning themselves right at the forefront of that wave, developing technology ready for chips that might still be on the drawing board, anticipating that 4000W future.
That's certainly how it looks. They're building the critical cooling infrastructure needed for the next generation of computation, preparing to manage heat loads that would have seemed utterly unmanageable just a handful of years ago.
Incredible stuff. It's so easy to get caught up in the capabilities of the AI models themselves, but the underlying hardware and the engineering challenges like cooling are just as critical to making it all function.
You got it. It's a classic engineering feedback loop. One system's incredible output, like massive processing power, becomes the next system's input problem to solve. In this case, that problem is just a staggering amount of waste heat.
And CoolIT is stepping up to handle it. Okay, this was genuinely fascinating, Mark. A really important, if maybe less glamorous, piece of the whole ACI hardware puzzle.
Glad you think so. It's definitely an area I'll be keeping a close eye on as these AI systems continue their relentless scaling.
Which brings up some interesting questions for our listeners too, perhaps. We've talked about the benefits and some of the challenges, like cost and complexity. What do you all think? Are these advanced cooling systems worth the investment? And where do you see the balance between raw performance and energy sustainability landing in the data centers of the future? Let us know your thoughts on our social channels or website forum.
Yeah, curious to hear what people think, especially if anyone works in or around data center operations.
All right, that's all the time we have for today on Tech Tangents. A big thank you to Mark for diving deep into the surprisingly cool world of high-performance liquid cooling.
My pleasure, Jenny. Always fun to explore the nuts and bolts, or perhaps the pipes and pumps.
Join us next time for another look at the ever-evolving landscape of technology. Until then, I'm Jenny.
And I'm Mark. Bye, everyone.